Initially, there was an infinitely dense mass of matter. This mass underwent an explosion that gave rise to the formation of atoms, molecules, stars, and galaxies that we can observe today. For decades, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests the universe does not have as early an origin as initially believed. Instead, it may be part of a cyclical process in which the universe goes through a series of cycles of expansion and contraction, possibly in an infinite loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. In addition, research from the James Webb Telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and answer this question and many more. If you're interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on notifications. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser approximately 13.8 billion years ago. During that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was as tiny as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this astonishing narrative aligns consistently with all current observations. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point at which our current methods cannot provide meaningful solutions. One of the indications of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests literally that the universe was once compressed into an infinitely small and dense state, which seems to be absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provide a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge, so we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an ekpyrotic universe, which takes its name from the Greek word meaning conflagration or fire. This idea suggests that the Big Bang, as we know it, was the result of an earlier event, implying that it was not the absolute beginning but rather a part of an ongoing process. Extending the notion of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photons in a vast void. The universe emerges from what, from another point of view, essentially approaches nothingness, although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one. The mystery lies in how the same state can be interpreted as both a cold, empty universe and a dense universe, depending on the point of view. The key to this understanding lies in a complex mathematical technique called conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the empty state and the hot, dense state can be connected through this scale transformation, aligning their spatiotemporal structures despite their differences in size. However, Penrose argues that the concept of size loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old, cold state to a young, hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time, since in these extreme states, both size and time lose their conventional meanings. The cold, empty state and the hot, dense state exist on separate timelines, which means that from the perspective of an observer within his own time frame, the cold, empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology concepts. Cosmology provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to ponder the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. For our purposes of discussion, we will focus on explanations within the realm of physics. There are three possibilities to consider in exploring the origins of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the option of a single cycle in a repeating universe, where the beginning of the cycle is explained by some feature of its own end. These possibilities are attractive because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. In the realm of physics, Penrose proposes the idea of an endless sequence of cycles, influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the remnant radiation of the Big Bang. As we delve deeper into the mysteries of the universe's origins and its potential cyclic nature, it becomes clear that our understanding is at a crossroads between empirical observation and theoretical speculation. The Big Bang theory has provided a remarkably coherent framework for explaining the expansion of the universe and the formation of galaxies, stars, and planets. Yet, it also leaves fundamental questions unanswered, particularly regarding what came before and whether our universe is just one iteration in an eternal cycle of cosmic birth and rebirth. Recent advancements in cosmology have led to competing theories that challenge the traditional narrative of a singular Big Bang origin. One such theory gaining traction is the concept of a multiverse, where our universe is just one of countless others existing simultaneously. This idea stems from theoretical extensions of quantum mechanics and string theory, suggesting that different regions of spacetime could give rise to distinct universes with varying physical constants and laws of nature. Within the framework of multiverse theory, each universe may have its own unique history, beginning with its own version of a Big Bang event. This scenario offers a potential explanation for the fine-tuning of physical constants observed in our universe, as it posits that only in a universe with specific parameters like ours could complex structures such as galaxies and life emerge. However, the multiverse hypothesis remains highly speculative and currently lacks direct empirical evidence. Critics argue that it may be difficult, if not impossible, to test experimentally, as interactions between universes would likely be beyond our observational capabilities. Despite these challenges, proponents argue that the multiverse provides a natural extension of our understanding of cosmology and could potentially resolve some of the persistent puzzles of the Big Bang theory. Another intriguing avenue of exploration is the role of dark energy and dark matter in shaping the fate of the universe. These mysterious components, which together constitute the vast majority of the universe's mass-energy content, exert gravitational influences that are crucial for understanding cosmic evolution. Dark energy, in particular, is thought to be responsible for the accelerated expansion of the universe observed in recent decades, a phenomenon that challenges earlier models assuming a slowing or constant rate of expansion. The nature of dark energy remains one of the most significant puzzles in modern physics. Current theories propose it could be a cosmological constant inherent to spacetime itself, or it could arise from more exotic phenomena such as quintessence, a dynamic field that evolves over time. Understanding dark energy is not only crucial for cosmology but also for reconciling observational data with theoretical predictions regarding the ultimate fate of the universe. In contrast, dark matter presents a different mystery altogether. Unlike dark energy, dark matter interacts gravitationally with visible matter and can be inferred from its gravitational effects on galaxies and galaxy clusters. Yet, its precise nature, whether composed of yet-to-be-discovered particles or modifications to gravitational laws, remains elusive. Resolving the nature of dark matter is essential for refining our understanding of galaxy formation, structure formation, and the large-scale distribution of matter in the universe. Beyond these mysteries lie broader questions about the nature of time and space itself. General relativity provides a robust framework for understanding gravity and the curvature of spacetime on cosmic scales, yet it encounters limitations when extrapolated to the extreme conditions of the Big Bang or within black hole singularities. Quantum mechanics, on the other hand, governs the behavior of particles and forces at microscopic scales, offering profound insights into fundamental interactions but struggling to reconcile with gravity in a unified theory. Efforts to unify these two pillars of modern physics, general relativity and quantum mechanics, have given rise to speculative frameworks such as loop quantum gravity, quantum cosmology, and string theory. Each of these approaches seeks to extend our understanding of the universe's earliest moments and its fundamental laws beyond the limits of current observational and experimental capabilities. String theory, in particular, proposes that fundamental particles are not point-like but rather tiny strings or membranes vibrating in higher dimensional spaces. This theory aims to unify all known forces of nature, including gravity, under a single mathematical framework. Within string theory, the concept of branes, higher dimensional surfaces, has led to speculations about the existence of higher dimensional spaces or bulk, where universes could be embedded and interact. Moreover, string theory allows for the possibility of multiple universes or brane worlds within this higher dimensional landscape, each potentially governed by different physical laws and constants. While still in its theoretical infancy, string theory offers a tantalizing glimpse into a more comprehensive understanding of the cosmos, where the Big Bang becomes just one phase in an intricate cosmic symphony. Philosophically, these explorations into the origins and fate of the universe raise profound questions about causality, existence, and the limits of human knowledge. The concept of cyclic cosmology, as proposed by Roger Penrose and others, challenges conventional notions of time and suggests that the universe's history may be more complex than a linear sequence of events. In Penrose's model, each cycle of expansion and contraction, driven by the conversion of mass into radiation via black hole evaporation, repeats indefinitely, with each cycle potentially altering the conditions for the subsequent one. This cyclical view not only offers a solution to the singularity problem at the Big Bang but also implies a continuous evolution of cosmic structures across vast cosmic epochs. Moreover, cyclic cosmology raises intriguing possibilities for the origins of cosmic structures and the emergence of complexity in the universe. If each cycle represents a reset and renewal of cosmic conditions, then the emergence of galaxies, stars, and even life itself could be seen as a recurring phenomenon shaped by the interplay of physical laws and cosmic evolution. From a philosophical standpoint, the idea of an eternal, cyclical universe challenges traditional views of a singular beginning or end. It suggests that the universe may be part of a larger cosmic ecosystem, where birth and death are not endpoints but rather phases in an endless cosmic dance. However, challenges remain in reconciling cyclic cosmology with observational data and experimental evidence. Detecting echoes or remnants of previous cycles in the cosmic microwave background radiation or gravitational wave observations could provide crucial insights into the validity of cyclic models and the nature of the early universe. In conclusion, the quest to understand the origins and nature of the universe continues to captivate scientists, philosophers, and the public alike. From the mysterious beginnings of the Big Bang to the speculative realms of multiverse theory and cyclic cosmology, each new discovery and theoretical breakthrough expands our cosmic perspective and challenges our assumptions about reality. As technology advances and new observational tools come online, the coming decades promise to unravel more of the universe's secrets and perhaps reveal whether our cosmos is just one chapter in a grand cosmic saga.